Hi everyone, we are ready for our first reaction in Unit 12, Conjugated Pi Systems. And before we do that, just a reminder, our first video was number 12, B50, and we introduced conjugated dienes, and we alluded to their special reactivities due to the delocalization of their pi electrons. So the reaction that I alluded to actually was the addition of HX, like HBr or HCl. But before we do that, I just want to go over briefly a little bit about allylic carbocations, because we're going to see allylic carbocations when we do this reaction. Allylic carbocations. We might have had practice with this when we first talked about resonance, or when we first talked about carbocations. And the allylic position, if you have a double bond, okay, let's draw a couple of carbons here. The allylic is the carbon off of the double bond. So the allylic carbons are this one, and this one. Okay. So we could add more carbons, but these are not allylic. If we have a carbocation on either of those carbons, we have an allylic carbocation. So let's force that. Let's do not a deprotonation, but let's remove a hydride off of this middle carbon right here. And I have that. That's called an allylic carbocation, and it's special because you have resonance. And the resonance that I can draw here is like that. And we have a second resonance structure that looks like this. Where's the missing plus charge? This carbon is naked because now it only has 3 bonds. We had 4 before, but we lost a double bond, and that's positive. Okay. That's all I want to say right now about allylic carbocations is that you have this opportunity to do resonance. This is very analogous, now that I think about it, to allylic halogenation when we looked at radicals. Right, the radical can shift. All right, for instance, this radical here, like that. Okay, remember it's a reaction where you use NBS. Okay, I'm not going to go through the whole thing, but yeah, you could have resonance like this, and you put the radical now here. Let me make it asymmetrical though. Okay. So we've seen that before. Just for completeness, remember when you use unpaired electrons, you have to use fishhooks. Okay, let us get to our first reaction and see how this concept of allylic carbocations help us. I actually thought of just one last thing. Sorry about this. Let's take a look at a very simple allylic carbocation, because remember last time in this video here when we introduced dienes, we were very concerned about the p orbitals, because the p orbitals, and when they align, that's what allows us to shift electrons because they're overlapping. Well, let's take a look at this allylic carbocation, very simple one, that. The exercise that we did at the very beginning of that first video was assign hybridization. sp2, sp2. Do you remember what carbocations are? Carbocations are carbons that have 3 bonds, no lone pairs. So if it has 3 bonds and no lone pairs, it has 3 balloons. Oh, this is also sp2. That's why it's so easy to have this sharing of electrons, because there's a p orbital right there to accept them. What was the other type of drawing that we had in the previous video? I drew the carbons sort of laying down, okay? And if each of those carbons are sp2, you know that each of these carbons has an unhybridized p orbital. Even the carbocation, because the carbocation is also sp2. So you definitely have a pi bond right here, and the pi bond is made with 2 electrons. But because we have a p orbital here, those electrons can easily shift over and occupy a pi bond to the left. Look at the result of this resonance. The result is the pi bond now is to the left, and we could have that. What am I going to put here? We only have 2 pi electrons in either case. So some professors don't like this. I don't mind. We could emphasize it's empty by putting a plus right there. And then when you have resonance, now the empty p orbital would be this one on the right. This one on the right. Okay? Okay, now I'm ready to look at our first reaction. Reaction Unit 12A. This is addition of HX to conjugated dienes. Now I'm going to put a little disclaimer here. For this video, we're only going to look at but simple examples where the conjugated dienes are going to be symmetrical. So we're only going to look at simple examples. And they're simple because these conjugated dienes are symmetrical. Don't worry, I'll show you examples where they're not symmetrical. But let's take a look at our first reaction. Okay, that is symmetrical because it doesn't matter whether I react due to the reaction on double bond A or double bond B, I would get the same products. The other way you could think about this is, I actually have a model of this, I think, I hope. The other way you could think about this being symmetrical is if you have that molecule, nope, sorry about this. If you have this molecule here and you make the model, you have basically that shape right there. And symmetrical because there is a point where you could rotate this and you have a plane of symmetry. So it doesn't matter which double bond you react. That's what I mean by simple examples. Okay? HCl. So, if you recall your unit where you did radical halogenation, many times, right, we would get more than one product. Most times we would get 2 products, one from the initial radical and one from the radical that you get from resonance. Well, we have resonance here also. A lot of times you could expect 2 products. The reason why you wouldn't get 2 products is if by some coincidence the 2 products are identical, which is possible in some cases. And we'll see if it's the same or if it's possible in this case. The 2 products you're going to get. Just focus on one of the double bonds. I don't care whether it's the one on the right or the one on the left. I'll do the one on the right because it's closer to the reagent. The first product that I would draw actually is this one here. Okay, don't worry, we're going to go over the mechanism in just a bit. The second one is this one here. Okay, I think some of you are recalling this exercise where you have to draw the product from the initial intermediate and you draw a second product from the resonance of that intermediate. Okay. You want me to show you what I did here? It doesn't matter which double bond you use. I used the one on the right. And I'm not drawing the mechanism right now, but I'm showing you where I got these two products. Because my first carbocation would place the carbocation on this carbon right here. It still follows Markovnikov's rule, right? The rich get richer, the H goes here. And remember, when I say the rich get richer, it's the money is hydrogen. So this has two hydrogens, it gets a third hydrogen. This only has one hydrogen, it's the poor one. Well, it got naked. There's no double bond, so it's positive. And now you'd see why we did that discussion on resonance, on allylic carbocation resonance. Because we get this carbocation now. And that's where I got the two products. Okay, that's where I got the two products. These two products have special names, several special names, but the one that I teach is, one of them is a 1,2 addition, the other one is a 1,4 addition. Find the double bond you're playing with, okay, and start numbering just the pi system. 1, 2, 3, 4. When I say the pi system, so let me take a look at here. This is the notes from the previous video. I'm labeling the 4 carbons that are sp2 hybridized. 1, 2, 3, 4. Okay, or if you use this double bond in the middle, 1, 2, 3, 4. Okay. So where's 1, 2, 3, and 4 in our products? 1, 2, 3, 4. Okay, now be very careful. See, that hydrogen added to carbon number 1. Carbon number 1 here. I'm holding the atom steady, so carbon number 1 is still there on the right. So I number it this way, 1, same way, 2, 3, 4. What did carbon 1 get in both cases? Carbon 1 got a hydrogen, right? Even when you have the resonance, that hydrogen is still there on carbon number 1. Look what got the chlorine. Carbon number 2 got the chlorine. Carbon number 4 got the chlorine. There are a couple of things I want to emphasize here, okay? The first thing is both. You got to make sure that you're making an allylic halide. Those are the coming from the stable contributors. Both of these are allylic carbocations. And then the result are two allylic halides. So both are allylic. What's wrong with my spelling today? Allylic halides. You could use HBr, HCl, even HI you could use. Okay. I think HF actually might be too inert, too unreactive. Use HCl or HBr. So both are allylic halides. Oh, and look where we're making the attachments. This is called 1,2 addition because we added hydrogen 1, chlorine on 2. What do you think this is called? This is called 1,4 addition. I know it's getting crowded, super crowded actually, and I'll just put here 1, 2 addition, and this is 1,4 addition. Would it have been possible to have both the 1,2 and 1,4 identical? Yes, there are some dienes where they would be identical, but I don't want you to memorize those examples. I want you to do these on a case-by-case basis. The vast majority of cases, you are going to have two products, the 1,2 and the 1,4. For now, you're going to draw both. Okay. I think I alluded to in the title that maybe we could control this mixture by adjusting the temperature. And I think I'll have time to show you that trick. But before we do that, let's do another example. In this video, I'm promising you just to do reactions on symmetrical dienes. Let's try this one. Let's try a cyclic one. Ah, this might be interesting. HBr. I know we didn't do the mechanism. I'll do the mechanism after this example. But let's see if we could do the example or do the fill in the product problem without drawing the mechanism. You have two double bonds, A and B. Again, why don't we work on the one on the right? So this is what's going through my head. I'm going to add HBr. Now this is weird. We don't have the rich, as in the rich get richer, because both carbons are equally substituted. They both have one hydrogen each. There is no rich gets richer. But we still use Markovnikov's rule in the sense that we make the more stable carbocation, right? This was the more stable carbocation because it's secondary allylic. I could have put the carbocation right here, right, if the H goes on carbon number 2, but that's only primary. Markovnikov, when it comes down to it, is really just telling you what carbocation to make. You make the more stable carbocation. Your two choices are this, okay? Again, we're using the double bond on the right, and this is scratch paper now. You could make this by putting the hydrogen on carbon number 2. Oh, why don't we do that? See, 1 and 2 are the carbons that I'm going to do the reaction on. It's conjugated to the 3,4 pi bond as well. So when we do the numbering for these conjugated dienes, I'm really looking for 4 carbons, 1, 2, 3, and 4. Okay. So we could have the hydrogen carbon number 2, which makes carbon number 1 the carbocation, or we can do the opposite, and we have that. Put the carbocation on carbon number 2. You see which one's more stable? They're both secondary, but this is secondary allylic. That's where my first product will be. Secondary allylic, bromine. Don't worry about stereochemistry. That is racemic, but I'm not worried about that for this unit. What I am worried about is if you think this is the carbocation that I should use, you have resonance. Okay, let's draw the resonance structure. And I have this. The plus charge is now there. Technically, where is it? It's on carbon number 4. Okay, so I'm keeping the numbering consistent between all of these 5-membered rings. The carbocation is on carbon number 4. The double bond got shifted, right, to do that resonance. Well, let me draw the product for this carbocation. I got this allylic halide by doing a 1,2 addition. I got this allylic halide by doing a 1,4. Do you see how 1 got the hydrogen originally? But now 4 gets the bromine. Let's number that. 1, 2, 3, 4. I'm going to call this the 1,4 product, or the 1,4 addition product. What do you notice about those two? In our first example, we got 2 different products. 1,2 addition, 1,4 addition. They're definitely not identical. Oh, no. These are identical, right? You know, don't worry about stereochemistry. I know we have RNS, but we have a mixture of RNS here and a mixture of RNS here. They're the same attachments. They're the same connectivities. These are identical mixtures. These two are identical, and you want to tell your grader that you know that. Because, again, if you draw 2 products, yeah, technically one is the 1,2 and one is the 1,4, but if you draw 2 products, you are basically telling your grader that you think there's only there's two products, but actually there's only one product. Okay, it's this product or this one. It doesn't matter which one you draw, or mark them both as identical. So this is an example where, yeah, we only get one product because the 1-2 edition and the 1-4 edition are identical. Should we do a mechanism? Let me actually do one more. Yeah, let me do one more. What about this? HCl. Yes, you have a choice. You can either make the tertiary carbocation, but it won't be allylic, or you can make the secondary carbocation and it will be allylic. You will always go for the carbocation that is allylic because resonance is such a stabilizing force. 1, 2, 3, 4. Have we done enough examples where you can see a pattern that you could quickly get to the product? Let me show you. 1-2 addition. Okay, 1-2 addition means I add a hydrogen on carbon number 1 and the halide on carbon number 2. Done. That is the 1-2 product from the 1-2 addition, but I'll call it the 1-2 product. Do you see how fast you could do these? How do you get the 1-4 product? You got to visualize, because if there's a carbocation on carbon number 2, that's why the chlorine went there, you could shift this double bond in the carbocation intermediate, and you would get what? The bond will shift over to the right, your carbocation will be right there. It's still allylic, but this is kind of cool. It's now tertiary allylic. Tertiary allylic. This is the 1-4 product. 1, 2, 3, 4. Okay. Why don't I do the mechanism for this? And I may or may not have time to talk about temperature control. Let's see. Yeah, so I'm using the diene, conjugated diene that we have up here. Again, you got to protonate or grab the hydrogen, but you have a choice to put the carbocation on either of those two carbons. You're choosing to put the carbocation so it is allylic and it has resonance capabilities. Plus Cl minus. Okay, so this brings up an interesting point. If I make the 1-2 product, I'm done. I have this. One, two. If I ask you to draw the mechanism for the 1-4 product, you can't, or if I ask you to draw the mechanism for both products, you can't use this picture here and draw resonance because you're putting two sets of different arrows on the same molecule. It's very confusing. So yes, you have to start anew and reform that carbocation. Not a big deal. Now I want to get to the 1-4. So yes, this is considered part of the mechanism, the resonance in this case. Just make sure that you know and that your grader knows that you know that this is resonance. So you have this double-headed arrow. But we need to draw this to be able to draw our 1-4 product. Don't draw your arrows from a charge, even if it's negative. Draw your lone pairs. That's my pet peeve. Okay. Most professors actually let you draw it from the charge, but I like to stay consistent and draw my arrows from a source of electrons. Literally, I see the electrons as a lone pair or a pi bond, or any bond. There's your 1-4 product here. Okay, let me tell you about temperature control. Between these two products, which one do you think is the most stable? Uh-oh. Actually, this is a bad example to do temperature control because the 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 most stable is also the one that's made fastest. When we use temperature control, I'll give it away right now. When we use temperature control, we are choosing typically either the more stable product or the one that's made faster. And a lot of times those are two different products. So let me do it with this example. An example for my exam will be pretty clear which one is the more stable product and which one is the faster product. Okay, let me draw this real quick. That's the 1,2 product. This is the 1,4 product. 1,2, 1,4. Okay, I'm gonna circle the major product. Oh, not the major product, the more stable product. Did I circle this one? It's weird because the carbocation was primary allylic, not secondary allylic. Because when you're looking at stability, you look at the final product and you base it off the double bond. So this is more stable because, do you remember your alkene stability rules? Tetrasubstituted is more stable than tri. Tri is more stable than di. Di is more stable than monosubstituted. This is disubstituted. So this is a more stable, not the carbocation that it came from, it's a more stable alkene. It's the more stable double bond. This one, though, has its advantages also. Actually, this one's made faster because you get to the carbocation intermediate faster because the carbocation is actually more stable in this case. One is faster, one is slower but more stable because one is depending on your analysis of the double bond, one is depending on your analysis of the carbocation. These have different names, not 1,2 and 1,4, but maybe you've heard of these names before. If it's faster, that is called the kinetic product. If it's more stable, we know that as a thermodynamic product. I'll let you digest that in just a bit, but there was a problem because I wanted to do thermodynamic and kinetic for these two as well. But in actuality, the kinetic and thermodynamic are the same. It's this product here. I won't have that type of example on my exam. It will be very clear cut which one should be the faster and which one is the more stable. This is clear cut because this is more stable because the double bond is disubstituted versus mono. This is faster because if you think about the mechanism, your carbocation initially was here, okay, a secondary carbocation, whereas here it became a primary. So the faster product is made via the more stable carbocation. So that's a little bit of confliction, right? Is that a word? There's a conflict. Which one's the major product? Because both of them have good points. The thing is, if they give you temperature, you're going to base it off the temperature. Under cold conditions, typically they'll put negative 78 degrees C. I think that's a dry ice and acetone bath. It drops the temperature. It's much colder than just ice water. You're going for the kinetic, always. Okay, and almost exclusively, I can't think of any examples. When you run this reaction under cold, your major is going to be the 1,2, and your 1,2 is almost always going to be the kinetic product. At room temperature or above, okay, you're going to favor the thermodynamic, and typically that's going to be the 1,4. Okay, There'll be practice problems, and I'll post the answers as well for my class. I know this was a lot for this one video, and I left a pretty complex concept towards the end. But try to understand this, and when you do the practice problems, I think it will become more apparent how to assign. Ultimately, I want to know what is the kinetic product, what is the thermodynamic product, and yes, when do you have the same one? You have the same one when you have a kinetic product, which is exclusively, I'm telling you now, is going to be 1, 2, okay? But it also happens to be the more stable alkene. And we had that situation right here, right? Isn't this the more stable alkene? This is tri-substituted. This is only di-substituted. So not only is this the thermodynamic product, I'm telling you that every 1,2 addition is the kinetic product. It's the one that's made faster. I think about it typically that what is the initial carbocation? Okay, the initial carbocation was the one that was first made, so it is the faster of the two. So the 1,2 product is always the product that came from that initial carbocation. Like over here, this was the initial carbocation. Okay, not a great example because it gives you the same product. But over here, our very, very first example, that's our initial carbocation. So let's label these two. Okay, this is the kinetic because it came from the initial carbocation, and the kinetic is always the 1,2. This is a thermodynamic product. It's typically 1,4, but not always. Not always. Sometimes the thermodynamic product is again the 1,2, just because of again the stability of the double bond. Okay. Sorry I went over, but for my class, that's all I want to discuss about this first reaction. And again, I'm not going to give you very complicated examples where the diene is not symmetrical. Let me give you an example, and then I'll be done. For instance, something like this. That's not symmetrical. It makes a difference whether I react at double bond A or double bond B. You will not see those types of examples. So this is not symmetrical. Alrighty. Okay. For my class, we have one more reaction, and I think I'm going to try to fit that all into one video. But that will be it for conjugated pi systems, just 2 reactions. All right. We'll do the second one in video, I believe it would be 12D50.